Here's a classic setup. X and Y are uniformly distributed over a disk of radius r. The joint density is 1 over pi r squared, everywhere inside x squared plus y squared less than or equal to r squared, and 0 outside. Think of throwing a dart completely at random anywhere inside a circular target of radius r. That's exactly this distribution. The question: what are the marginal densities, f of x and f of y? To get a marginal, we integrate out the other variable. F of x is the integral of the joint density over all y. But here's the catch: for a fixed x, y can't range over everything. It's trapped inside the circle, so the limits of integration depend on x. Fix x somewhere between minus r and r. Solving x squared plus y squared equals r squared for y gives the chord's endpoints, y equals plus or minus the square root of r squared minus x squared. So the integral becomes 1 over pi r squared, integrated over y from minus that square root to plus that square root. That's just the density times the length of the interval. The bracket evaluates to 2 times the square root of r squared minus x squared. F of x equals 2 over pi r squared times the square root of r squared minus x squared for x between minus r and r. Here's the step where the surprise hides. The width of that chord shrinks as x moves away from 0 toward plus or minus r. Intuitively, near the middle, y has lots of room to range over. Near the edges, the chord shrinks almost to a point, so x near plus or minus r is far less likely. That means the marginal is not uniform, even though the joint density was constant everywhere on the disk. So the marginal is a semicircular density. Tallest at x equals 0, tapering smoothly to 0 at the edges, x equals plus or minus r. Check that it integrates to 1. The integral of the square root of r squared minus x squared, from minus r to r, is the area of a semicircle of radius r, pi r squared over 2. Multiply by the 2 over pi r squared out front, and the r squared cancels exactly, leaving 1. By the same symmetry, f of y has the identical semicircular shape, 2 over pi r squared, times the square root of r squared minus y squared. Contrast this with a rectangle. If the support were a rectangle instead of a disk, the chord length would be the same constant value for every x, so f of x would in fact come out uniform. The deeper lesson: a uniform joint density gives uniform marginals only when the support is a rectangle with sides parallel to the axis. Change the shape of the region, a circle, a triangle, anything else, and the marginals pick up the shape of the boundary. So what would the marginal look like if the support were a square instead?